Okay. Hello everyone and welcome back to some late night entropy with Anthony. Now in this video I'm going to be looking at part C this time. So we're going to be demonstrating numerically that for a given average and standard deviation that maximizing the entropy of a discretized probability distribution yields the normal distribution. Okay, so we're going to look at how maximizing entropy causes a trend toward a normal distribution. So we're just going to go ahead and jump right in. Now, if you remember our, our entropy, if you remember from the last video, that equals the sum of the probability, so probability, times the natural log of that same probability. And it's actually the negative sum. Now, of course, I'm not typing this in correct notation here. I'm just so we can remember what this is. So this is what entropy is, and again, we solved that in the last part. So we want to maximize this, and to do that, we're going to use this scipy.optimize.minimize. Now, of course, this, as you might expect, minimizes. It does not maximize. So what we're going to do, we're going to remove this negative, and we're going to minimize that. We're going to minimize the inverse. So I'm going to code this in real quick. So np.sum, np.log, and np.log defaults to log, natural log. So return and we will define entropy. Takes in the probability and return that. So like I showed above, or up here in this tab, scipy.optimize.minimize. So we want to import that. So from scipy.optimize import minimize. Shift enter, shift enter. And now let's take a look at this minimize function. First things first, we want to give it a function to minimize. So of course this is going to be our entropy. So function equals entropy. We are going to need to give it a guess, an initial guess, x naught. Now, so in order to give it an initial guess, we're going to have an initial. Okay, well, if I run that, of course, it's not going to work. We want to have an initial guess, so I'm going to call it p naught. And p naught, that's going to be our initial guess of probabilities. So I want to say that for every grade, so we'll put a line above here, the number of possible grades is actually going to be 11. 0 through 10 ends up being 11. Now I'm going to put this into an array called grades, and that's going to be equal to np.range and the number of grades. And what np.range does is it just sticks this 11 here. It just makes it into an array. So for this initial guess, we're going to use np.full, and I have this pulled up here. It basically returns an array of given shape filled with the fill value. So we'll give it a shape, and we'll tell it what the fill value is. So the shape will be the number of possible grades, and the fill value will be our initial guess. So I'm going to say the initial guess is 1%. There's a 1% chance for every possible grade. Then down here, we'll put in our initial guess. Now we want to add some bounds. So for doing the bounds, we're going to want to put, let's look here. Bounds, specify the bounds. So we want to put it in as a min and a max. So we'll do that like this. Bounds equals, we want it to go from 0 to 1, but we basically want to scale it by the number of grades. To scale it up to basically making sure it can fit all the different possible grades in there. So that'll be our bounds. And then finally we need constraints. And we're going to have to come up with some constraints for this. So we're going to start by writing some functions for constraints. And I think the most obvious is that our probabilities all have to add up to equal 1. And I think that that's fairly obvious. That's just the definition of probability. The probability, they will all add up to be equal to 1. So the sum of all p's must be 1. So we'll return the sum of all the p-values, and that should equal 0, or it should equal 1. But actually, since we're minimizing, we want our ideal outcome to basically spit out a 0. So when np.sum, when the sum of all probabilities equals 1, we're going to subtract 1, which will spit out a 0. So the way the constraints work is we want to give it brackets, and we want to basically give it a bunch of, fill it with dictionaries. I believe we want to specify a type of constraint, and if I look here, the constraint types are either an equality or an inequality. So these will be an equality. And then we need to give it, we need to call the actual function. So function, and then I specified psum as the function. We'll go ahead and run that. Okay, and it spits out, it basically gives us all this stuff. We care about this, that's stored in the x here. It's an array. It tells us every grade has a probability of about 9%, which is a uniform distribution. So actually, I want to graph this. So I'm going to store this as our distribution variable. Now we want to make a figure. We're going to use plotly. Make subplots. And then dot add bar. And we want our x to equal grades and our y to equal the probability of getting that grade. So distribution.x. That'll give us those x values that we saw before. Okay, and here we go. It's a normal distribution. So what this is saying is that for these possible grades, given that all the probabilities have to add up to 1, the maximum entropy outcome looks like this. So of course it will change. We're going to give it some more. We're going to give it some more constraints. So we want to give it an average and a standard deviation. So we'll start with the average. So define average. Now, for the average, it's going to be the sum of all the different grades that can be had divided by the total number of students. So if we multiply the probability of getting a certain grade multiplied by that actual grade multiplied by the number of students, the sum of all of that divided by the number of students, that will be the average. And of course this n here, those actually cancel, which is very nice. It simplifies things. We don't actually need to know how many students, or we don't actually need to know the number of students. It doesn't matter for this average. It's just going to be the grades times the probability, np dot sum, and we will return that. So then I'm going to add in another constraint here. Just copy and paste it. And instead of p sum, this constraint will be average. And if we remember from before, this needs to spit out a 0 as the ideal value. So if we say, we'll give it an average of, let's say, 5. So 50% is the average, using a score of 50. Or I guess 5 out of 10. When we graph that, it actually gives us the exact same distribution. Now, I think that might be due to me giving it a 5 here. Let's say if I were to give it an 8, the average is an 8. Okay, so it's weighted a lot more heavily towards these higher scores with this average of an 8. Okay, so this is working. That's a good sign. Now we want to give it a standard deviation. So define standard deviation. It's a function of probability. And so if we look at the grades we actually get, if we were to subtract it from the average, so the grade that is had minus the average, square it, that is the, I guess from the definition of standard deviation. We would want to weight it by multiplying by n times, or the number of students multiplied by the probability. That would give us more of a weighted average. We would want to sum all of that. So np dot sum. And we would want to divide by n. And again, we have an n in the numerator here, an n in the denominator, so we can just get rid of that. It doesn't matter. And then we want to take the square root. So use np dot square root. And then that should be the standard deviation. So we will return that. And we'll say standard deviation of 1.5. Because again, we want it to spit out a 0. So I will copy this one more time. We want to add a new constraint. And we will use std, shift enter, shift enter, shift enter. And g is not defined. I must have forgot to type in grades here. Another error. What is going on here? Unsupported types. Did I type this in the wrong way? Unsupported operand types. Maybe it's this. I'm not sure exactly why it's getting mad at me. Let me look at this for a second. Type function. P times grades times minus average, minus 1.5. I wonder if it's upset because I didn't define average. Maybe I need to define it within this function. Let me define average in here. Oh, there we go. Okay, so, I mean, this looks kind of weird. But it looks like we have an average of 8 with a standard deviation of 1.5. Oh, with a 1. Sometimes this thing's a little finicky. It might look better if I give it some more data points. So I'll give it 101 possible grades, so you can get 0 through 100. We'll say that the average is a 50, and the standard deviation can be a 15. Oh, wow, that looks really nice. Okay, so this is the normal distribution. Centered at 50, standard deviation of about 15. And this was done completely by minimizing this entropy function up here, this probability times the natural log of the probability, or the sum of all of that. Minimizing that was able to give us the normal distribution. So I'm just, let's say I put in 1,001. Give it a, let's give it a average of 750. Let's say the standard deviation is 40. Oh, it's going. Uh-oh. Maybe I gave it too much. Maybe I gave it too much. Uh-oh. Yeah, okay, we won't do that. I got a little bit too excited there. We'll just stay with 101. There's 75 and, I don't know, 12. Okay, yeah, I mean, this is really nice looking. This is the normal distribution. So there we go. Part C, demonstrate numerically that for given average and standard deviation, that maximizing the entropy of the probability distribution yields a normal distribution. And we can see that very beautifully here. So thank you for watching, and I will see you in the next video.